Okay, guys, now I want to talk about how we can solve that integral. I told you the easiest way to do it is just to look it up in an integral table. So that's what I'm going to show you how to do here. Let me go back and show the full solution again. Okay, the full integral that I was trying to do looks like this guy here, right? For this particular problem, I just kept this bit, okay? So I'm throwing out some of those constants just to make it a little bit simpler. Okay, so I'm going to try to figure out how to do this integral. Again, I can throw the x out here, outside the integrand, because x does not depend on y, okay? So what I'm showing here is a integral table. So I just Googled integral table. This is the first website that came up. And I'm just scrolling through it, scrolling until I find an integral that looks like the one I'm trying to solve, okay? And I think I probably scrolled too far. And it's under this, for this one, it's integrals with roots because I'm taking what's in the denominator to the 3/2. So this down here, number 41 is the integral that the part of the integral table that's going to show me how to solve the integral that I'm looking for. If I look here, for that one, if I want to transform it from what's in the table to what I have written, I have to realize that x there is the same thing as y for me, and a in that particular table is the same thing as x. Okay, so if I look at the solution over here, I end up getting x out front. Okay, because I had that anyways. And then my integral, I'm going to end up getting y on the top because y is the same thing as x in that table. I'm going to get an x squared out here because x for me is the same thing as a in that table. And then I get the x squared plus y squared, okay? And then that is equal to the 1 over x. And then I got the y, x squared plus y squared. And remember, I got to take that from y equals L to y equals 0. Okay, so this hopefully shows you how I can use, this shows you how I can use an integral table to get this here, okay? All right, so that's how I use the integral table. That's obviously an easy way to do it, and hopefully you guys have some familiarity with that from other classes. I'm going to close that up. Let's actually just do the integral the harder way through substitution, okay? All right. So let's think about how we can solve this integral through substitution. So I'm going to erase this for a second. Okay, if I look at this integral, and if I look at another integral table, it will give me a hint about this substitution. I want to do what's called a trigonometric substitution. Okay, which means I'm going to take the x squared plus the y squared to the 1/2, and I'm going to substitute in r for that. Okay, and then if I look at the geometry of the problem here, I'm going to define this angle theta. This is x, this is y. I recognize that the tangent of theta is going to be equal to y over x. Okay, and if I think about my rod being here, instead of integrating over y, I could also integrate over a range of thetas, and that will give me the same thing. It'll still sweep across the rod. Okay, so what I want to be able to do is take the dy part of my integral, and I want to write it as a d theta because now instead of integrating over y, I want to integrate over theta, okay? So the way to do that is to take this relationship that I already recognize. Okay, I'm going to rewrite that as y is equal to x times the tangent of theta. And then if I take dy d theta, I get x is equal to 1 over cosine squared of theta. That's just the derivative with respect to theta. So that gives me dy is going to be equal to x over cosine squared of theta d theta, okay? So now I need to also get the rest of my integral in terms of either r or theta. I'm going to start with this part here. I've got x squared plus y squared to the 3/2. If I factor out the x, then I get that value there, okay? So I just factored out the x, and I can rewrite that in terms of theta, because x over y is the same thing as the tangent of theta. Okay. It turns out that 1 plus the tangent of theta squared is the same thing as the secant squared of theta. So that's something I could look up in a cheat sheet with trigonomic identities, right? And that's the same thing as 1 over the cosine squared of theta. So in general, I can simplify this guy here to the 3/2 as x to the 3rd, or 1 over the cosine squared of theta. If I put that all together, okay, remember I started with x, 1 over x squared plus y squared to the 3/2 dy. I put that all together, I end up getting, let's see, x to the 1 over x to the 3rd, 1 over cosine to the 3rd theta, and then I get an x over cosine squared theta d theta. Okay, so this is from me transforming the integrand. This is from me transforming that dy. Okay, I can, again, put this all together. Still, if I look at all of the x's, and remember I can pull the x out of the integral because x does not depend on y. It also doesn't depend on theta. I end up just getting the integral of cosine theta d theta, okay? And that's going to be equal to, right, 1 over x times the sine of theta. Okay. If I want to keep going, I could either refigure out what the limits are in terms of theta, or I could recognize that that's the same thing as 1 over x times y over r. That's what the sine of theta is equal to, which is the same thing as 1 over x times y over x squared plus y squared to the 1/2. Okay, so we're basically back where we started. The whole integral is equal to 1 over x times x squared plus y squared to the 1/2, and I'm going to take that from y equals L to y equals 0. Okay, so that was just a lot of math to show you I can get to the same place I got before again, all the way back here using substitution. Okay, again, this is stuff you guys should be practicing more in your math classes than in your physics.